Welcome to Homework Lib.
Hi, so in this problem what we're going to have are 2 mole of a diatomic gas that has initially a pressure one of 111 kilopascals, an initial temperature of 277 Kelvin, and that is going to be heated reversibly to a second temperature of 356 Kelvin at constant volume. And for this process, we are asked to calculate delta U, delta H, Q, and W. So, first of all, in order to calculate Q, the result for that is directly doing the integration of NCV dt. So, since we are dealing with an ideal gas, meaning we have a diatomic gas molecule, so we can treat them as an ideal system, this is going to be equal to NCV delta T. So for an ideal gas, the value for Cv is equal to 3 halves of R. So this becomes Q equals N 3 halves R delta T. In our case, N is equal to 2. So our heat would be 3 times R times delta T. This becomes 3 times 8.314 joules per mole Kelvin. Oops. Per mole Kelvin. Remember that we have already multiplied by 2 moles over here in this section, so we can get rid of the moles. And multiply by the delta T. And the value for delta T in this case is 356 minus 277. So a delta T of 79 Kelvin. The heat coming from this reaction is equal to 1970.418 joules. Now, what is going to happen with the work? Actually, before we start with the work, let's go ahead with the definition for du. And this is going to make things quite clear. So remember that du is equal to dq plus dw. And this is equal to dq minus pdv. So, as you can see, the value for dw is equal to 0 if the change of volume is equal to 0. So the work is going to be 0 in every process that has a constant volume. And as a consequence of this, we know directly that du is equal to dq. So the change of internal energy is directly q. Delta u is equal to q. So delta u would be 1970.418 joules. Now, for the very last part, let's do what's going to happen with enthalpy. And for that, we need to do an extra calculation. So we know the initial pressure, we know the initial temperature, but we know what is going to be the final pressure, and we are going to need that at the very end. So remember that P1 is equal to nR T1 divided by volume. So P2 is going to be equal to nR T2 divided by volume. So if we divide P1 by P2, P1 over P2, the result is equal to T1 divided by T2. So we can calculate P2 directly as P1 times T2 divided by T1. In this case, P1 is 111 kilopascals, T2 is 356 Kelvin, and T1 was 277 Kelvin. So my final pressure for this process would be 142.657 kilopascals. Now, with this information, we can go ahead and do the calculation for the enthalpy. Recall that H is equal to U plus PV. This means that dH would be du plus PdV plus BDP. If the change of volume is equal to 0, this is 0, so dH is equal to du plus BDP. Integrating, delta H becomes delta U plus B times change of pressure. And what is going to be the volume that we're going to get? Well, that is going to be simply the volume that we had initially, because we're told that the process is heated at constant volume. So the volume is equal to nR T1 over P1, and equal to R 8.314 joules per mole Kelvin. T1 is 277 Kelvin divided by P1, that is 111 kilopascals. So we need to multiply it by 1000 to get the result in pascals. And the volume result will be in, since everything is in international units, in the international system of units, the result will be in cubic meters. You can verify it by checking that a Pascal is Newton per meter squared and introducing the definition as well for the joule. So the volume is going to be 0.0415 cubic meters. The other information that we required was delta P. We know that this is going to be P2 minus P1, and this is equal to 31,657 pascals. Pascals times cubic meter is going to be in units of joule. So delta H would be the value for delta U that we already calculated, plus B times delta P. This is, I'm going to 0.0415 cubic meters times delta P, 31,657. I'm going to write down pascals and Newton per meter squared. Meter squared with cubic meter, we end up with meter. Newton times meter is going to be joules, right? So delta H is equal to my value for delta U, 1970.418 joules, plus 1313.7655 joules. The result for delta H is thus 3284.1835 joules. And with this, the problem is complete. You have the values for delta H, for delta U, Q, and W. Just to summarize, let me close everything in red. The value for Q, the value for W, the value for delta U, and finally the value for delta H. And that will be all. Thank you very much.